So what else could affect enzyme rate and reaction rates? We have to think about now not so much environmental conditions, but the actual enzyme itself. So is the enzyme degraded? If the enzyme is degraded, it's not going to work right. Okay? We need a good enzyme that's well built. What about the amount of enzyme? If you have more or less enzyme, how is that going to affect the reaction rate? Well, more enzyme means you can do more reactions, right? So the reaction rate goes up. What about if you have a different amount of substrate? Maybe you have the perfect amount of enzyme, but your substrate is very low. So if your substrate levels go down, what's going to happen to your reaction rate? Think about it like hide and seek. If you're an enzyme trying to find a substrate and there are very few substrates, they're going to be harder to find, right? The reaction rate goes down. The last thing you should think about is if there have been any modifications to the protein or the enzyme. And we'll look at these more later on, but things like the addition of different functional groups will cause an enzyme to behave differently. So all things to kind of keep in mind. There are always things that want to interfere with enzymes. We call them inhibitors, things that are going to stop the enzyme from working properly. We can have competitive inhibitors. If you compete for something, what are you doing? You're essentially working directly against something, right? You're fighting against something, you're fighting for something. These are actually inhibitors that are going to block the active site. This is really important to keep in mind because when we talk about competitive inhibitors, they're directly interfering with the substrate enzyme complex. So with our competitive inhibition, the inhibitor looks like the substrate, meaning that its three-dimensional shape is probably very similar. It fits in the active site. It gets in the way. It has to fit there. Okay? An example of this in you is the nerve gas sarin that actually has a very similar three-dimensional shape to acetylcholine. Acetylcholine is something critical for you to use, and actually binds to the enzyme itself. So it's acetylcholine esterase, the enzyme itself. So sarin's going to bind to the enzyme, blocking your ability to actually produce compounds necessary to continue functioning, in particular associated with your heart. That's a pretty critical thing to be blocking, right? The non-competitive inhibitors, actually block at a non-active site. So I mentioned to you that some of these enzymes are so large that they actually have multiple active sites. So in this case, we're blocking at a non-competitive site, or what we call an allosteric site. Let me show you. Competitive inhibition directly blocks. So our substrate is this yellow thing. It wants to fit into my enzyme. This blue thing, while it's not exactly the same as the yellow, it has a piece of it that will fit into this enzyme and completely block it. Different, we can look at it just blocking part of the active site. It doesn't matter as long as it's interfering with the active site of target. So this is the active site. As long as it's interfering there, the competitive inhibitor, it's a competitive inhibitor. Non-competitive or allosteric inhibitors actually are going to bind with something other than the active site, like we said. So in this case, our yellow substrate can't bind because this green non-competitor has come in, entered a different site, and changed the shape of my enzyme so that my substrate no longer fits. We see this quite a bit as well in different systems, and the idea is you've got some change in shape. This comes back to the idea that shape is critical. We have to keep track of three-dimensional shape, and in this process, look at how it might impact reactions. Now, competitors are not always bad. The competition that we are looking at here is actually something known as negative feedback. In this case, my enzyme is turning yellow round substrates into orange triangles. And it's going to keep doing that all day long if that's its job. But the problem is, continuing to make a whole lot of orange triangles that you don't need is a waste of energy. So just because enzymes decrease the amount of energy needed to be put in doesn't mean they make it zero. So why do this? The idea with negative feedback says if we build up too many orange triangles, an orange triangle is actually going to act as a non-competitive or allosteric inhibitor. And when it does, it changes the shape of the enzyme. The yellow ball no longer fits, and we stop making yellow circles into orange triangles. When do you think we'll start again? When we run out of orange triangles. When this concentration of orange triangles goes down, this inhibitor falls out, and we go back to where we were at the beginning, yellow circles into orange triangles. Often we see this coordinated in something known as a metabolic pathway. This is the conversion of substrates into some product that we need that can't be done in a single step. So in the first step, we're going to actually combine two substrates. So this yellow and this orange are going to come together in enzyme A. Enzyme A's product is this kind of fingernail looking thing. It fits then into enzyme B. Exactly. Enzyme B's job, it's got this little nub sticking out here, is to actually cut off part of this substrate. So that's gotten rid of. This product of enzyme B then moves on to enzyme C. Enzyme C folds it into a boomerang. Now, this is very picturesque, of course, of what is going on, but the idea is these kinds of pathways occur all the time. And you see these enzymes are sitting across a bilayer, right? Our plasma membrane. So this is occurring in your cells all the time. When we look at these enzyme inhibitors regulating metabolism, as we mentioned to you, we can get that feedback inhibition. And when we get feedback inhibition, we get some regulation of this process based on product. So if you increase product, you decrease the reaction rate. They aren't all this pretty. Sometimes this product can actually slow down this second reaction step or this third reaction step. It doesn't have to turn it off from the beginning. And the reason I say that is in something like this, which is actually regulation of glycolysis, or the beginning of cell division, or cell respiration, pardon. So at the beginning of cell respiration, we all go through glycolysis, which starts to convert some of the glucose into a form that can be broken down and used for energy. Every place you see a hash sign like this, it means it can stop the reaction. Every time you see this up arrow, it means it can increase the reaction. So we have excitatory and inhibitory processes going on here all day long to help regulate the rate at which this reaction goes. Please don't memorize this. What else affects enzymes? Well, there's one last thing I want to tell you about, and that's what we call cofactors, coenzymes, and prosthetic groups. So cofactors are things that are in your vitamins, zinc, copper, iron, and so on. These are actually going to help work with the enzyme to make the enzyme reaction go better. And typically we see cofactors working with the substrates, and we see coenzymes, kind of as their name implies, working with the enzymes. So ATP, we said that sometimes these enzymes need energy. It would get it from ATP. Vitamins might work with enzymes. These other things, these prosthetic groups, so a prosthetic addition to these enzymes would be something like heme. Where have you seen that before? Hemoglobin? So this is actually a group that's permanently bound to an enzyme. So it's heme plus enzyme gives you hemoglobin. What's hemoglobin's job? Carries oxygen in your red blood cells. So pretty critical for functioning in you, and looking at how they kind of work together to really get through this process of using enzymes to regulate reaction rates.